Right. Welcome, everybody. So today it's my pleasure to welcome Wesley Marrero, who is joining us from his he recently joined the School of Engineering at Dartmouth. Before that, Wesley was at Mass General Hospital, prestigious postdoc fellowship. And before that, he did his PhD in Industrial Operations Engineering at the University of Michigan under the supervision of Professor Maria Lavieri. And Wesley, and I hope I didn't mess this up, has two interests on the methodological side is at the intersection of simulation and stochastic optimizations, and he'll talk a little bit about this today. And on the application side, he has, I think, a wide range of applications, primarily in healthcare, including cardiovascular disease, organ transplantation, and substance. Wesley, and welcome to our speaker.
So, excellent. Thank you, Gabriel. Really appreciate the intro. Yeah, all right. Excellent. So I timed this presentation. I like that the group is quite small. We can make it a little bit more intimate. I timed it for 35 minutes. We should have plenty of time to have conversation and just talk about things. Please feel free to stop me at any point. I do not mind having a conversation. Today I'm going to be presenting part of my research. I'm very excited of providing flexibility to decision makers. That's the principle behind this presentation. Instead of providing a single optimal solution, which makes perfect sense mathematically, but it might not be able to be implemented in practice. So instead, we provide alternatives, choices for people to choose from. And I title it Simulation-Based Sets of Similar Performing Actions in Finite Markov Decision Process Models. If you're familiar with Markov decision process models, this is, if you're not, sequential decision-making framework. So we're going to be making decisions sequentially. All right, so instead of talking about these concepts in the abstract way, very mathematically and obscure, I chose to put everything within the context of cardiovascular diseases. And we're going to be using the treatment of atherosclerotic cardiovascular disease as the motivating example. And the reason for this is that ASCVD or atherosclerotic cardiovascular disease, is the leading cause of death in the U.S. A little on the older side, but this still holds true today. And it's composed of two things. Stroke, which itself, it still is among the leading causes of death, is in the top 5 in the U.S., and coronary heart disease, or CHD, which accounted for approximately 43%. Yeah, 43% of deaths due to diseases of heart. And my collaborators and I strongly believe that the management of improved by providing flexibility to physicians and their patients. So let's start at the beginning. What do I mean by a set of similar performing actions? It is a set of actions that are not statistically different from some action of interest at some significance level. So I want you to go back to your stats 101 class when you have this magical value, alpha, that pretty much establishes your level of risk. And to understand this definition, let's consider the following example. Imagine that you have 6 different treatment choices. Again, thinking within the context of cardiovascular disease treatment, ranging from no treatment to 5 medications. Say that you're treating hypertension, like in the case study. And say that 3 medications, if your action of interest, let's say is the optimal action, if you have some model of the environment, or perhaps is the action that some guidelines recommend. If we find 2, 3, or 5 medications are not statistically different from each other, we say that these 3 actions or number of medications are a set of similar performing actions. And here I want you to notice that 4 medications is not included. We have a gap. There's a hole in the set. Later in the talk, we're going to be considering the special case where this cannot happen. And I call that a range. So all the actions are consecutively ordered. Within our context, all the medications have to be consecutively ordered. So if 3 and 5 are part of the set, 4 has to be part of the set as well. All right, so at this point, you might be thinking to yourself, well, you're talking about statistical inference. You're talking about statistical significance. What is the source of variability? And to answer that question, we need to go all the way back to the data that we're using to parameterize our model, which I haven't described yet. And within our context, that's people's data. Patients' demographic information, lab and overall health conditions, whether or not they have had a cardiovascular event in the past, let's say. Based on this information, we make a risk prediction. Based on this risk prediction, we make a treatment selection. And this treatment selection can have many outcomes in terms of the patient. A patient may remain healthy. They might experience a coronary heart disease event, like a heart attack, or they might experience a stroke, or something else. And that is going to be our source of uncertainty. So based on an estimate of some model of our system of interest, we're going to be using the variability in the outcomes for our statistical inference. And why do we need flexibility? You might be asking to yourself, why does it matter? So what? Cool, this is cool math. Why is it important? Why is it useful? Well, it happens that since the late 90s, and probably before, to almost till today's date, has found that physicians, they just don't follow guidelines. Maybe they can't, or maybe they just won't. They have their own opinions, their own procedures. They have their own biases and preferences. And the reason for this is that treatment selection depends on their judgment, but also their patients' preferences and opinions. And ASCVD, or cardiovascular disease, more generally speaking, is not the exception. One of the main controllable risk factors for cardiovascular disease is hypertension, or high blood pressure. And this itself is a problem within the US, as we estimate that approximately 46% of adults have some form of hypertension. And researchers have found barriers to the implementation of guidelines. And since the early 2000s, almost to today's date, physicians' judgment and patients' preferences play an important role in treatment selection. So with this in mind, we are focusing on hypertension treatment, so the management of high blood pressure, and we model the sequential process of giving antihypertensive medications as a Markov decision process. Based on conversations with my collaborators, we chose a planning horizon of 10 years. Most clinical guidelines, since perhaps the last 2 decades, have focused on 10 years over the life of patients. And this is what happens in practice as well. For whatever reason, physicians consider the next 10 years to decide today's treatment for a patient. Oh, and decisions are made every year at the beginning of each year. Our states are patients' demographic information, laboratory measurements, so blood pressure readings, cholesterol readings, and their overall health condition to account for history of cardiovascular events. Actions are from 0 to 5 antihypertensive medications at half dose and full dose. And this gives a total of interaction space. Our transition probabilities were derived from the medical literature. And here we are acknowledging that these are not completely known. This is just an estimate. And it's a combination of patient's risk for cardiovascular events. So here we're dealing with personalized medicine, or precision medicine is called in some places. The mortality from these events, mortality from something else that is not ASCVD related, and the effect from treatment. So how much blood pressure reduction and risk reduction from a medication. Our rewards are the expected quality of life weight, so how well, a measure of how well someone is at the current year, at each decision epoch, minus treatment harm to account for side effects of medications. And the terminal condition are people's life expectancy after this 10-year planning horizon. Does this model make sense? You guys are too quiet. Any questions so far? Yeah. So it's a basic subtraction. They are in the same units of the qualities in this utility kind of function. So for each blood pressure medication at standard dose, in the medical literature, they have assigned a quality adjusted life years of 0.01. So you're losing 1% of perfect health, basically. We good? Please. Correct. Yeah. At each decision epoch. Mm-hmm. Yeah. So that leads to an infinite. We were actually discussing this. That leads to an infinite state space. However, when you project the health trajectory of someone, this reduces. So let's say you use some supervised learning method to project the health trajectory. This reduces to the 10 health conditions that we're using. So healthy, cardiovascular events, and death, and over 10 years. So it reduces to 100 states in the state space. Correct. Each patient, we don't care about certain spaces if the patients don't have that particular blood pressure or cholesterol readings. They're irrelevant for the decision-making process. So yeah, that simplifies things. That makes things tractable and highly manageable. All right, excellent. Okay, so with this in mind, my team and I generated 2 ways of providing flexibility. The first one is, let's say we have some policy of interest. Things can be better than policy. The second case is the very special one that we know that our policy of interest is optimal. The remaining actions have to be worse than the optimal. We also relax this to an approximately optimal action. So you do not necessarily need to know the optimal to deal with this case. All right, so let's now dive into the first case. Similar performing sets to some action of interest. And instead of dealing with some action of interest, let's focus on what the current clinical guidelines say. So our action of interest is going to be whatever the clinical guidelines say. In summary, they're way more complicated than this, but in summary, they give a recommendation depending on groups of patients' blood pressure. And the groups are defined in the bottom of the slide. We don't have to get into it. If the patient has elevated blood pressure, they do not recommend any meds. They recommend non-pharmacological treatment. So exercise, diet changes, less alcohol, less smoking, and behavioral changes in general. If the patient has stage 1 hypertension and their 10-year risk, here the 10, the magical number, 10-year risk is above 10%, we provide treatment until the blood pressure is below whatever stage 1 hypertension means. And in stage 2 hypertension, pretty much the same condition. Once the patient crosses the 10-year risk, we're going to provide medications until the blood pressure is controlled, is below the stage 1 hypertension levels. And with this framework, we had 3 things in mind, 3 main goals. First, design personalized sets of similar performing actions. So this is a more abstract methodological goal. Understand how the sets change according to each patient's characteristics, and understand how this translates to a whole population. What are the impacts of this within the US? So let's dive into the first goal. Design personalized sets of similar performance. So how do we do this? How do we design these sets? Within our context, this starts, as you might be thinking, with data. This starts with patient's demographic information, blood pressure, cholesterol levels, smoking status, overall health condition. Based on this, we model their health projection to have this manageable Markov decision process, and we use an approximate dynamic programming, recognizing that our transition probabilities and rewards are just estimates. We're deriving them from data. They're not our absolute truth. To estimate our expected health each treatment choice, assuming that we're going to use the guidelines in the future. And here we make this assumption because they're always going to be close to the guidelines. All the sets that we're going to develop are always going to be not very different from the guidelines. And moving on in the future. Then we take the output of this algorithm as an input into a statistical multiple comparisons with a control method to identify treatment plans that are not statistically different from the guidelines. So we identify the performance of the guidelines, we fix them as controls, and then we do the statistical inference around that control. Lastly, we combine these two things, and we get what I call sets of similar performing actions, which may be very nice and consecutively ordered, very intuitive, everything makes sense, or they might be like the ones on the slides that have these jumps that no one understands why. So let's dive into the approximate dynamic programming. For every year, for decision epoch, more generally, state and treatment choice or action, we're going to need the following. Next year, estimate of action value function. And within our context, those are the average life expectancy of the patient at the next year, starting with their terminal condition, which is their life expectancy after the planning horizon. Based on this input, we're going to simulate a bunch of health trajectory. And we're going to record the performance of each medication. So we're going to record the outcome of each health trajectory at each. These trajectories are mutually independent. We can use parallel computing to execute this. And this results in huge computational gains. At the end, we're going to get our estimate of action value functions for today, for this decision epoch, which, within our context, are the average life years for each health state and treatment choice at the current year, assuming that we're going to follow the guidelines in the future. Again, we always want to be close to those guidelines or our action of interest, some policy pie. Any questions about the algorithm? All right. Correct. Approximate policy evaluation. Yeah. Not yet. Yeah. Policy evaluation on the first, that's a great way to put it. Policy evaluation in the first half of the talk. Optimization, or approximate optimization on the second half. All right, so now we're going to move into the statistical multiple comparisons method. And for every year, health state and treatment choice as the input, we're going to need the output of the first algorithm divided into batches. And within our context, these are the simulated life years for each health state and treatment choice divided into segments. So essentially, we're using the output of our first algorithm as a data set and perform statistical inference on that. Based on this input, we're going to calculate this absolute value of a standardized, what the guidelines are saying, and the remaining alternatives for each of these batches. And since when you fix our control, all these batches are conditional independent, you can also use parallel computing to implement this. And this runs pretty fast as well. And at the end, we're going to get an estimate of a quantile. And this is the quantile that we're going to use to identify treatments that are statistically different from what the guidelines are saying, or whatever policy evaluating. All right, but why do they work? What's the logic behind this? The first algorithm is just a simple extension of the strong law of large numbers. If you have enough samples and you take an average, the average tends to converge to the expected value. That's the logic I'm using here. And in plain English is that we can simulate enough health trajectories to ensure that the average life years attained by the algorithm at each year is the true value almost always. The second algorithm works because of this proposition that establishes that the probability of our event of interest will be exactly our desired confidence level for large enough number of simulations. And in plain English, we will achieve the right coverage in simultaneous confidence intervals if we simulate enough health trajectories. So if we're able to observe enough trajectories or potential of patients' health, we should be able to achieve this coverage. All right, so let's now move on to the second goal of the talk. Let's try to understand how these sets change with the input data. In our case, how they change according to patients' characteristics. And to understand this, let's consider this patient. A 40-year-old patient with stage 1 hypertension. Here in the x-axis, we have the planning horizon, 10 years over the life of patients. In the y-axis, we have hypertensive medications. The circles represent the clinical guidelines, and the blue area in between are our sets of similar performing actions. So for this particular patient, we have sets containing from 8 alternatives all the way in the beginning to 2 alternatives. And this jump around here in year 8 is because the patient reached the 10% 10-year ASCVD risk. So the guidelines become more aggressive. They start treating. Now, if we change the blood pressure to this patient to stage 2 hypertension, the sets become smaller. The cardinality of the sets reduces. And let's say we make this patient older, to 60 years old. The cardinality reduces even further. In general, we notice that patients with a higher risk get less treatment options, which makes sense in clinical practice. If someone's very sick, you want to be very careful with how you treat them. But if they're pretty healthy, there's more room to play with. Did that make sense? Sure, please. The guidelines are the control according to them. If they're crazy, the sets go with them as well. Now that being said, and this is something I'm going to talk in a few slides, we did notice that for some people the guidelines are over-treating patients and under-treating older patients. Yeah. Any additional questions? All right, okay. All right, so let's talk about the population level. How does this translate to a big chunk of people? I use data from the National Health and Nutrition Examination Survey, or NHANES. This is allegedly a nationally representative data set of the US. And I took a sample, a representative of people with ages 50 to 54. And the reason I did this is because this is an age group that can benefit greatly from hypertension treatment, and they're still at high risk of cardiovascular events. So we put out quite a bit of thought to this population. We imputed any missing values. We wanted to be representative with it. I expanded the data set according to their sampling weight, so every record has they represent X number of people, and then I generate a synthetic population. And for this synthetic population, I forecasted their untreated blood pressure and cholesterol readings. This is to reduce our state space, going back to our initial conversation. And this gives a total population size of 16.7 million people. All right, these are the main results. Here in the x-axis, we once again have the planning horizon. Y expected life years saved per 1,000 people. And we chose 3 different alternatives in the sets. Given the fewest number of medications, given the median number of medications in the set, and given what appears to be the best according to the number of trajectories we have generated. And the reason we chose these alternatives is to represent people that hate medications at different levels. If someone really dislikes medications, you go with fewest number of medications. This research shows that this tends to increase people's adherence. So they actually take the medications. If someone is very afraid of a cardiovascular event or very concerned for their health, you go with the best potential medication in this set. And if someone is in the middle, we just go with the median. And for a comparison frame, we also included the clinical guidelines. And here, you can notice two things almost immediately. The first thing in the set is very similar to the guidelines, at least in the first two categories, elevated blood pressure and stage 1 hypertension. And also, the median in set and the best in set outperform by a lot the clinical guidelines. In stage 2 hypertension, things get less clear. They perform quite similarly. And that led us to think, basically your question, what's happening in the treatment? And to answer that question, we started to look at the distribution of our actions. Here, the x-axis represents the different blood pressure categories. Y-axis represents the number of medications. And each of the boxes are the best in set, median, fewest, and clinical guidelines. Here, it is clear. We're definitely treating more aggressively. That's why we have this huge gap. However, in stage 1 and stage 2 hypertension, there's a lot of overlap, which is an indication that we're just not treating more aggressively, but we're treating people differently, which points to the hypothesis that maybe the clinical guidelines are over-treating some people and under-treating other people. All right, and that concludes the first part of the talk. Before we move on, any questions? All right, I hope I'm not being very boring or too confusing. All right, so let's move on to the second part. Similar performance, please. Uh-huh. Yeah, per 1,000 people, yeah. Yeah, it was too much to include everything in the same scale. All right, so let's take a moment to compare the first and second part of the talk. Policy of interest, which I was using the clinical guidelines for our controls, our action value functions. Now we're interested in what appears to be the best according to our number of samples. Similarly, with the next year action value functions, we go from some policy pi to the maximum. Our distribution of interest becomes easier to deal with. We go from a two-sided distribution to a single-sided distribution. So we remove the absolute values. And now we're interested in this idea that I briefly mentioned at the beginning of the talk. We want the actions to be consecutively ordered, to be intuitive, to make sense to physicians. And I spent some time identifying sufficient conditions to guarantee this. All right, and the research goals, pretty similar. Designed what I call now ranges, understand how the ranges change, and the implications at a population level. Let's dive into the first one. Very similar framework. Start with people's health, proximate dynamic programming, you can also call it reinforcement learning with a particular exploration policy. Multiple comparison, we get a set, now with no gaps. The main difference is that now in the future we are assuming optimal, or realistically approximately optimal, what appears to be the best. And the same thing in the multiple comparisons with a control. Now our statistical inference is one-sided. We have an upper bound. We cannot, theoretically, asymptotically speaking, we cannot go above the optimal. Well, can go equal, but only worse. All right, so for this, I got a little bit more excited, and I spent some time studying the finite sample properties and the asymptotic properties of both algorithms, including the two results analogous to what we saw in the first part of the talk. However, the convergence, once you fix this maximum, instead of some policy of interest in the approximate dynamic programming, it doesn't come for free anymore from the strong law of large numbers. You need to do some tricks. But the proposition of the coverage of the convergence intervals is actually easier to prove because you only deal with one-sided comparisons. All right, so when do we get these ranges? What are these conditions? To answer that question, I spent some time studying the asymptotic structural properties. So here, all these results, they hold for a large enough number of observations. And if you're wondering about that large enough number of observations, you can definitely check out my paper. There's a particular sample path for the convergence. And we're going to focus on theorem 3, the attainment of the ranges of near optimal actions. And again, I want to remind you, sets, we have gaps, ranges, everything's consecutively ordered. It makes sense. People like it. So when do we get it? It happens that if we can order the immediate rewards and the transition probabilities, particularly the tail distribution of the transition probabilities, according to the states and actions of the MDP, we're guaranteed to get ranges of near optimal actions with probability 1 for large enough number of observations, or asymptotically, if you just like things to go to infinity. And to understand the implications of this theorem, let's consider the following example. Imagine that you have a plus 1 number of alternatives, and that action 4 is your optimal action, or what appears to be. We compare action 3 to action 4. Let's say that it is not statistically inferior. We add it to the range. We compare action 2. It is not. We add it to the range. Let's say we compare action 1, and it is. It is statistically inferior to action 4. We exclude it from the range, and we do not need to compare action 0. It must be statistically inferior because we have this nice ordering. Let's say the same thing happens with action 5. We exclude it from the range, and the range must be statistically inferior as well. So a range of near optimal actions provides two types of benefits. First, it makes sense. People like them. They trust it, which makes it, hopefully, more likely to be implemented in practice. Second, there are computational benefits. You need to make less statistical comparisons, which makes a big impact if you have large action spaces, with the understanding that this is for finite. Does not deal with infinite. All right. Let's now move on to the second part of the second goal of this part of the talk. Let's see how these ranges change. And they pretty much behave pretty similarly. Imagine that you're dealing with a non-diabetic patient with stage 1 hypertension and low cholesterol, 54-year-old female. Here, the green circles represent the optimal policy. The purple diamonds represent the clinical guidelines. This patient has less than the risk. Year one, x-axis once again is the year, the planning horizon. Y-axis once again is the number of antihypertensive medications, standard and half doses. And the blue area in between are ranges of near optimal actions. And if, let's say, we change the sex of this patient to male, we observe narrow ranges. We also notice that now there is a difference between the clinical guidelines and the optimal policy. Now the clinical guidelines are definitely inferior, or at least they appear statistically inferior. We're pretty sure. We make this patient a smoker, they become narrower. And if they make this patient older, even narrower. So the same behavior, basically. Patients with higher risk get narrower ranges, which again, it makes sense in clinical practice. All right, let's now move on to the third part, or the third goal of this part. Quantify the implications of flexible treatment plans at a population level. Very similar point. X-axis planning horizon, Y-axis expected life years saved. The same three alternatives. Best in range now, medium in range, fewest number of medications in range. Now for point of comparison, we also added the optimal policy and the clinical guidelines. And here also two very fast observations. The fewest in range behaves pretty similarly to the clinical guidelines. And the best in range behaves the same. And the reason for this is that the optimal policy assumes that the transition probabilities are known and the rewards are known. Our method does not make that assumption. We just need sample observations. And for this, we also started asking, why? What's going on? Are we actually over-treating people, or we're just treating people differently? And that was exactly the case. Here in the x-axis, we have the type of treatment strategy, the number of medications, and an overlap across all policies. So we're definitely just not giving people a bunch of medications. We're treating people differently. We're identifying people at high risk. And the clinical guidelines are failing to do this. So the clinical guidelines might be over-treating and under-treating other patients. All right. So with this, I would like to summarize and present some conclusions. First, I presented two new frameworks to obtain sets of similar performing actions. The first one, to some policy of interest, things can be better or worse. The second, when you know that things are optimal, at least in the limit. These methodologies match or outperform current hypertension guidelines for giving options, giving alternatives to physicians and their patients. And this may have many benefits, not just in clinical practice, but in practice in general, like better user experience and flexibility. These topics. The first part is going to be appear in the proceedings of this winter simulation conference, and there is a preprint available on the second part. It's still under review. With this, I thank you all for your attention and your questions. Please.
Hello? There we go. Okay.
Yeah, that would work. Yeah.
So, sorry. So when you showed the graph of the smoker, I saw the clinical, the recommended clinical had a little jump there.
Mm-hmm.
Just a small point of clarification. So like in
the treatment recommendations are made on the basis of risk, not only blood pressure. And smokers have higher risk, so the treatment indeed changes if you just started smoking.
Okay.
Even if your blood pressure is the same.
So does the doctor have a sheet, like if a person comes in and they have this blood pressure and they smoke, informative of the, sorry, it's just like.
No, it is. It is
okay.
important.
Okay.
It is important. They don't necessarily have a cheat, but there are online tools to calculate people's risk.
Okay.
And there are cheats for what to do according to each risk. There are like these. You might even have seen it in like doctors' like doors, like these like posters. If you have this risk, you should do this. If you have this other risk, you should do that. But yeah, that's how the same thing happens if someone as well. So yeah, it fundamentally changes your trajectory
Okay.
in your health.
Thanks.
Yeah, thank you.
Is it assumed that the medications have an order? So like if you have 5, A, B, C, and D, and E?
So It depends on us as modelers. We might, so here I only presented number of medications, and the order is pretty clear. So 0, 1, 2, 3, 4, 5. But when you talk about drug type, you might order them according to their risk reduction. Let's say that you have 2 medications, and in the first case is drug type A and B, and in the second case is C and D. You could order. It depends on us how we define the ordering. Like in a sister project of this, I'm dealing with drug types as well. And what we did is that we ordered them according to risk reductions. So it can extend to beyond just the natural ordering of number of medications. It depends on us and the user at the end. But yeah. Thank you.
I have a quick clarification question. So when you compare, like to test if two policies are statistically equivalent, you compare their final cost function, like a statistically equivalent, like what statistics are you comparing for different policy? And do you have assumptions of the distribution of the statistics you are using, or you proved as a distribution?
Yeah, no, I make no distributional assumptions. That's one of the things I try my best to avoid, because there's no reason to believe that something like Q values, the action value functions, will follow distribution. What we are comparing is, I call it a standardized difference. So basically, imagine a t-test. Mm-hmm. That is basically the same statistic that we're comparing. So if we have two different alternatives, and one has a t-value of, I don't know, 2.1, and the other one has a t-value of 3, the one that we use for the statistical comparison is the maximum of those two, so that the simultaneous confidence intervals cover both. But at the end, it's simply a difference between the difference of action value functions of our control or alternative, the true value, which we do not know, we're estimating of our control or alternative, divided by the standard error. That is the function that we're using to get our statistical significance. It's pretty much an extension of multiple comparisons in classical statistics. Thank you.
We're done?
Yeah, one more.
Okay. So no, it's maybe we'll see. Great talk. I know you kind of like went over some of the technical details, kind of like in the interest of accessibility, but I'm kind of interested maybe a little bit in what's under the hood. So for the first kind of method, strong law of large number kind of results, and even the uniform law of large number results, you're assuming something about like sufficient excitation in there, right? So is there kind of like something in the way that you're running the simulation, something in how you're doing that like policy evaluation where you're ensuring that stuff is sufficiently explored?
Yes. So here with finite sample size, I'm assuming a kind of an idealistic exploration strategy where you can explore the whole action space. This is not practical in large states and action spaces, but because we're dealing with parallel computing, we can deal with pretty large state and action spaces and still like observe everything.
Number of state action combinations that you're dealing with when you're doing this policy evaluation. Like, what are we talking? Like,
well, for this, 100 states, 21 actions.
Okay.
And it runs like 10 to 12 seconds.
Sure.
Typically.
Okay.
But when we're dealing with like bigger action spaces and state spaces, you still get good estimates. I mean, if you know the optimal, in a matter of less than a minute. basically.
Okay. The other part that I'm like curious about, the guarantees that you have for like the second method, because it kind of, so very similar to like results from like Whittle's index and like Gittin's index, where if you can show that stuff is decreasing, you kind of recreate the same kind of sets. Is that kind of what's going on? But
That
there's,
is
like,
basically the,
some
yeah.
specific structure here, or is it very similar to kind of like a regular kind of Markov bandit situation?
We weren't making any assumptions. So the only assumptions that we're making are finite MDP, so finite states, actions, and decision periods, and finite rewards. They need to be bounded.
Right. Yeah.
Other than that, we make no assumption on the
and then
structure.
indexability, right? That when you combine the state action pairs, you have an ordering, right?
Yes, and some ordering of the actions according to the states. Yeah.
Right.
Mhm.
Yeah.
Yeah, but on the second,
Yeah.
on the second part, to get the bolt and the plus sign
Yeah,
and
yeah,
whatever,
yeah.
there we're assuming the indexability.
Yeah, that's what I'm saying. That's
Okay,
that's
okay,
what I
okay.
was
Yeah, to get a
asking,
range,
right?
yes, you need that ordering.
You okay.
Yeah.
Okay. Gotcha.
But you can still implement the method. It's just, it's not going to be
Right.
intuitive.
Yeah,
It's just,
that's-
you can get anything. Yeah.
Yeah. Okay. Makes sense. All right. Thanks.
All right, sweet. Thank you. I think we have one more. Yeah.
So with respect to you cited like instances where doctors in a certain direction.
Yeah, no, that's a,
And how
that's
do
a,
those
that's a great
policies
question.
evaluate?
In short, we don't know. It's all over the place. I spent some time, I had a similar question myself. I spent some time shadowing cardiologists to see what they do. Same cardiologist with different patients, according to their conversations, they might overshoot or undershoot. Like typically it goes with patient's tolerance to medications. Like it really is, if someone hates to take medications, doctors are going to give a little less than what the guidelines are saying. And if someone is very afraid of a heart attack, they go over. So it really depends on what the doctor thinks is going to work with the patient and the patient's feedback. So there is like a behavioral game in there. It's very complex. Yeah, thank you for the question.
Save the best for last. No, I'm just joking. No, I had just a couple, coming back to Catherine's question. So when you mentioned the ordering that gives you these structural properties, I think when you say that rewards according to what that was the ordering you were using.
Yeah, so the ordering is in the same sense of monotone policies in the classical MDP setting. So within this context, what it means is that you're gonna provide medications or treatment that is for a sicker patient that is at least as intense as the one that you're providing for a healthier patient.
So it could change with that ordering may change with the patient, or is it still?
No, in general, it holds. So if someone's sicker, doctors tend to treat them more intensively, unless they have very strong side effects. There are some people that get some very bad swelling, and or just don't want to take more medications because they're combining with other conditions. But in general, the average case, the sicker the patients, the more aggressive the medication. And that's what I'm assuming here. That is the ordering that I'm referring to. But in general, the more severe the state, the more intense the action.
Okay.
That I'm assuming that like direct relationship between the state and action spaces.
Oh.
That
Just a
makes
quick-
sense? Yeah.
that makes sense. And I'll follow. Then you had batching, right? Because you
Uh-huh.
have strong law of large numbers, and the way you sort of arrange the simulation is like batching. And just wondering for students in the class, what that meant for, or maybe the.
Yeah. So this goes back to your question. It's like, how do we get away with doing statistical inference without any distributional assumption and without bootstrapping? If you know what that means, bootstrapping is a resampling technique. So here, since we are assuming that either you have a simulator, you have an estimate of like maybe a system of equations of how the system evolves over time, or you can observe things over time. What we did is that we divided things into chunks. Let's say that we had 100 observations, and I made 10 batches. So each of the batches will have 10 different observations, and for each of these batches, I calculated different statistics. So this is a way to study the uncertainty of the process without any resampling techniques and without making any distributional assumptions. That's the idea of batching. Thank you for that question. You have clarified it, yeah. Anything else? All right. Thank you. Yeah. Gracias por todo, Gabriel. My mic's still on.